Welcome to week 5 of structure analysis 1 taken by Professor Amit Shaw. I am Trisha Chakravarti, course teaching assistant. I am a first year PhD student at the Indian Institute of Science, Bangalore. We start with a brief recap of the weeks so far and what we have covered. In week 1, we looked at the basic types of internal forces, which is bending moment, shear force, torsional moment, and axial force. And then at the common classification of elements and boundary conditions, commonly real life structural elements are classified as beams, frame elements, trusses, based on the kind of idealization we do for each of them. And boundary conditions can be hinge support, fixed support. We start with a brief recap of the previous weeks. In the first week, we first looked at the types of internal forces, the basic four types: bending moment, shear force, axial force, and torsional moment. Then, at the common classification of the real life structural elements, based on how we idealize them, for example, beams, trusses, frames, and boundary conditions like hinge support, roller support, fixed support, and internal hinges. And at structural indeterminacy, which is an a very important concept of structure analysis. And finally, we looked at the bending moment diagrams and shear force diagrams of beams. In week 2, we moved on to trusses. We first looked at how to idealize truss, how to idealize a 3D real life truss into two-dimensional trusses, then stability of trusses, and then solving the member forces in a truss. There are basically two methods: method of joints, method of sections. And in week 3, moved on to the second kind of structural response. There are two kinds of structural response: the force or stresses, and the displacements or the strains. So for that, we first looked at the principle of virtual work and the unit load method to determine displacement in trusses. In week 4, we looked at deflection of beams using two methods: elastic curve equation method, where we would use double integration to obtain the equation of the beam, of the deflection of the beam along the axis of the beam, as a using double integration of the governing differential equation, and the moment area method, which is based on two theorems. And there is another method that is used for deflection of beams, which we are going to look at today. That is the conjugate beam method. There are some common terminologies in beam theory that we covered in the last class, but just to briefly mention, because they repeat here as well. There's a neutral surface in a beam. That is, a beam is formed of many fibers aligned longitudinally, like this. Longitudinal means along the axis of the beam, under the action of downwards or upwards transverse loads. Basically, transverse loads are the ones we expect a beam to have. So under the action of downwards transverse load, the fibers near the top contract, that is, they become smaller, and the ones near the bottom becomes longer, they extend. And there is one plane in between somewhere here where the fibers of the beam do not change their length. That is called the neutral surface. It is a surface because a beam is a three-dimensional body. So this is the surface that goes into the plane, and the neutral axis is this line. If we idealize the beam in a two, if we look at the beam in a 2D plane, then this line will be the neutral axis, and the neutral surface is this line going inside into the plane. And the axis of the beam is the interaction of the neutral surface and the longitudinal symmetry. And the deflection curve is when the beam is loaded, the neutral axis of the surface deforms into a curve, which is called a deflection curve or elastic curve. It is basically written as a function, as a function y of x, where x is the distance along the axis of the beam and y is the vertical deflection. And the deflection varies along the length of the beam. At any point, at any given x from one of the ends, we can find out the deflection y. Now we start with the look at the conjugate beam method. In this, this is basically a structure analysis technique that is used to analyze beams and frames by transforming the real beams into imaginary or conjugate beams. Basically, there is no diff. I mean, there whatever method we use to derive the elastic equation, like the y of x function, from whether we use the double integration method, where we get it as a function y of x, a continuous function, where plugging in any value of x, we can get the y. That is one. Using the moment area theorem, we don't get a continuous equation. in the moment area theorem we get the we take 2 points A and B, and then we consider, and then using manipulating the choice of A and B, we can get the deflection or slope at any particular point. So technically, we using that we can technically get the slopes and deflection at any point along the longitudinal axis of the beam. And similarly, in the conjugate beam method, we don't get a continuous equation as such, but we can get the deflection and slope at any point along the axis of the beam, and these methods will all give equivalent results. They have no, I mean, it does not, the result does not depend on the choice of the method. But this is a the conjugate beam method is probably the easiest one to use, because there are some set rules that we have to just follow. So the first thing is that we the real beam is has to be converted into an imaginary conjugate or a conjugate beam using the rules. So then on that conjugate beam we can apply the principles of virtual work and static equilibrium to solve for the unknowns. The basically the unknowns are the bending moment shear force and the deflection and the slope. And the bending moment and shear force we already know how to find out, that we covered in week 1, and that is one of the most important topics in structure analysis in any exam, as well as it will be needed all along a person's civil engineering career. And deflections and slopes are what we are trying to find out here. So there is the principle of duality between real beams and imaginary beams. That is how, now we are given a real beam. A real, if we are given it, that means that we have its dimension, we have its loading condition, we have its boundary conditions. Now we have to conjure up an imaginary beam that will also for. I mean, it will look like a real beam. It will have the similar boundary conditions, similar loading conditions, not same, but if you are given an imaginary beam, that can also pass off as a real beam. Like, and also principle of duality is like a real beam that you convert into an imaginary beam, and if you consider that imaginary beam to the real and convert it into its imaginary, you will get back the real beam. So they are dual. This is the principle of duality. The real beam is subjected to loads and support conditions that we are given already, and it is transformed into an equivalent imaginary beam called the conjugate beam. Now that this conjugate beam has the same length as the real beam, which they see there are other, a beam is basically a three-dimensional body. It has three dimensions: the length, the depth, and the width. The width is into the plane. So when we are considering a two-dimensional body, we are concerned about the length and the depth. But here, like when we found out shear force diagrams and bending moment diagrams, it was only the length we were concerned about. We did not even consider the depth of the beam, though it will have significance later on. So basically, when you draw the conjugate beam, you will draw it in the form of a line, like we draw normal real beams. So it will have the same length, and it is subjected. The conjugate beam is subjected to loads equivalent to the bending moments along the length of the real beam. So equivalent, this term equivalent is like, it is not self-explanatory. So these are the rules that you have to follow, and the transformation simplifies the analysis process. Obviously, that is why we are doing it. If we convert it into a conjugate beam, we can very easily get the displacement and slopes. These are the rules for loading in conjugate beam. The M by EI diagram of the real beam is the load on the conjugate beam. The M is the bending moment. So you know how to draw a bending moment diagram in a real beam. That you will get some shape. It can be linear. It can be constant. It can be linear. It can be 2 degree, 3 degree, any kind of curve. You divide those values by EI. For example, if the peak value, if it's like a straight line triangle whose peak value is 180 units of moment, like kilonewton meter, then you have to divide it by EI. Then the diagram will look exactly the same, but it will be divided by EI, and that diagram will be the load on the conjugate beam. That basically that shape. And the sign convention is the same as that of bending moment diagram. We know that. Yes. Do you have anything to say, Sonu Gautam? I can't hear you if you're saying anything. Okay, if you have anything to say, write in the chat box.
Ma'am, I want to ask that what is the difference between movement area method and conjugate wheel method, ma'am?
Basically, there is no difference. I mean, the way we are tackling the problem is different, but the basic concept is the same. But it is just the conjugate beam method is just a different way of arranging the moment area method. Like in the moment area theorem, if I tell you to get the if I tell you, give me the deflections at points, 3 points, any 3 points a b c I mark in the beam, and I tell you, give me the slope and deflection at those 3 points, then you have to apply your brain in deciding what pairs you will take to apply the moment area theorems. Okay, like maybe you will take a and one of the support points, and from that you will draw a tangent, because you know the support. Suppose the support is a fixed one, then we will know the slope there is 0, and you will find out at a, then maybe you will take between a and b. It is a slightly lengthy method if you don't know exactly the choice to take, and moreover if more than 1 points you have been asked. And in the conjugate beam method, it is just the area moment theorem arranged in such a method with mechanical kind of rules. Like you just have to follow the rules and you will get it like directly. If you know about the this conjugate beam method, I mean, I haven't started that yet, like how we get there, but you probably know about that. So you know that you can get it in a single shot. Like you draw one conjugate beam, and then you can get the point, get the slopes and deflection at any point, I say, with that single shot. So that is why, in unless you are very experienced in using the area moment theorem, it is preferable to use the conjugate beam method. When, of course, when in a time bound exam like in gate or anything, you have to look for the shortest time, right? The concepts are the same, the basis is the same, it's just an arrangement, a framework to use it directly. Okay. Okay. So the sign convention is the same as that of the bending moment diagram, like we did earlier. This is like when we are coming from the left side, clockwise moment bending moment is taken positive. When we are coming from the right side, the this anti-clockwise moment is taken positive, and vice versa. So that is how we will just draw the bending moment diagram with its sign the way we used to. We will draw with plus minus written, and that is what the sign will be like. If there's a positive or sagging bending moment, for example, in a simply supported beam with a UDL pointing downwards, we will get positive moment, we will get a sagging bending moment diagram of parabolic nature. So there then the load on the conjugate beam will be downwards, sorry, will be upwards, because that is positive or sagging bending moment. And for negative or hogging bending moment, it will be downwards load. For example, in a cantilever, we know that in a cantilever beam with a tip load or with a UDL load pointing downwards, we get negative moment. So in the conjugate beam, that diagram will be the load in the downwards direction. So this is an example. If this is a real beam diagram for positive moment, like this is the M, then this M by EI, this will just be scaled by a factor of 1 by EI, and the load will be upwards because this moment is positive. This is the conjugate beam diagram for deflection and slope analysis. These are the rules for boundary conditions in the conjugate beam. See, to make up an imaginary beam using from the real beam, we need, what do we need? We need the length of the beam, which we are saying is the same as the real beam. Then we need a loading condition, and then we need the boundary conditions. So we have looked at how we give the load, and now we look at the boundary conditions. Okay, so if in a real beam we have a fixed support means deflection in the transverse direction is restrained and rotation is also restrained. It becomes a free beam, free end at the conjugate beam. Like, and a free end basically means that moment at this end and shear force at this end is zero. Like in a during bending moment diagrams and shear force diagrams, we saw that by the time we reach a free end, both the bending moment and shear force diagram have to go to zero. And similarly, since I said this, using the principle of duality, everything has to correspond to each other. Like in the real beam, if there's a fixed support, in the conjugate beam, it is a free. Similarly, in the real beam, if you have a free end, in the conjugate beam, you have to replace it by a fixed support. And hinge support stays the same. Hinge and roller, they stay the same in both. A hinge or a roller support basically is equivalent in a beam, because in beam we don't allow axial displacement. So transverse deflection is restrained and rotation is freely allowed. And similarly, in a hinge support, moment is zero. Since rotation is freely allowed, there can be any theta. The moment at a hinge support is zero, which we again saw during bending moment diagram. We saw that in a hinge support or a roller support, the bending moment has to go to zero. But the shear force is non-zero. Obviously, it will the shear force is non-zero. That means it is giving a reaction basically. A roller support or a hinge support gives a vertical reaction, right? So that is the shear force. And if there is a middle support, that is also called a knife edge. It is like not at, if there is a hinge, this is acts as a normal hinge, but it is not at the end, so this is called a knife edge or a middle support. That converts into a middle hinge, that is an internal hinge. And what this knife edge, we have not probably encountered it too many times before. This knife edge basically means that vertical displacement will be zero because it is a hinge, it restrains the downwards or upwards deflection. And rotation is allowed, but the theta on this side and the theta on this side has to be equal. This is what we saw when we were using the double integration method to get the equation of deflection, like y as a function of x. These were the continuity or compatibility conditions. Like if at this point the theta on this side and the theta on the right, left and right are not equal, then there will be a discontinuity in the beam, and that we cannot allow. That is not a compatible solution, and that can never happen. Just like equilibrium has to be satisfied, some another condition that always has to be satisfied is the compatibility or continuity conditions. So if there is a knife edge here in the real beam, it will become an internal hinge in the conjugate beam. And by the principle of duality, if there is a internal hinge in this, there will be a knife edge here. And here again, just this is how the moment at an internal hinge, the whole point of internal hinge is moment becomes zero there. But and the shear, there is a shear moment transfer between the two sides, like from the left to right there will be a shear force transfer, but it has to be continuous. It has to, I mean, on the shear force on just the left and just the right of the internal hinge has to be the same. This is an example. If you're given a real beam like this, which has a fixed support and it has a point load at this tip, then uh, what we have to see, the length will remain 12 feet. The length is remaining 12 feet. Now we need the bending moment diagram. What will the bending moment diagram here be? This the At this point, like firstly the bending moment diagram will be linear because there is only a single point load. If there is a UDL, we know the bending moment diagram becomes a parabolic in nature. Now this the moment at the support is 3 kilopounds into 12 feet, that is 36. So 36, and it is negative because it is hogging moment. We know that from the sign convention, coming from the left, clockwise moment is positive, but here we are getting anti-clockwise moment. So this is the negative moment. M by EI diagram will look like this. It will start from 0 at A and end at 36 by EI at B. Of course, these are the units that you have to follow. You have to keep in mind. And so, in this real beam, in this conjugate beam, the length will remain 12 feet. The loading will be in the form of a triangular load, like in the downward direction. It will be exactly like this shape. This shape is replicated here. The magnitude also here will be 36 by EI. And this was a free support. A was a free support in the real beam, so A has become a fixed support in the conjugate beam. And B was a fixed support in the conjugate beam, so it has become a free end in the in sorry B was a fixed support in the real beam that has become free in the conjugate beam. So we have this conjugate beam. Now what is our ultimate end? We want to find out the deflection and slopes, right? The deflection and slopes of the real beam. So now we are going to look at why we drew this conjugate beam. From that, how we can get the slopes and deflections. Here there are the rules for extracting response of real beam from the conjugate beam. The bending moment diagram at any section of the conjugate beam is equal to the deflection of the elastic curve at the corresponding section of the real beam. And so what does this mean? If I tell me the deflection at this midpoint, at this 6 feet, like 6 feet from either end, tell me the deflection at this point. What do I have to do? I have to find out the bending moment of the conjugate beam at this point. That we know how to find out. We don't have to draw the entire bending moment diagram. Maybe like if at multiple points I ask, if I say give me at several points, like give me at 3 points somewhere, like 2 feet from here, 2 feet from here, and the midpoint, then maybe it will be helpful to just draw the bending moment diagram. If you draw that, then you can get it in one shot, like all the three. But if I ask only at one point, you simply have to find out the bending moment at this point. And what does it say? That the bending moment at any section of the conjugate beam, like at this section, Section is like section is a point that is at certain distance. I mean, any point in the beam is called a section. It is called a section because it's like we are cutting a section along the along the cross section of the beam. Here, since we are working in one dimension, it doesn't really make sense to call it a section. You can call it any point. So if we find out the bending moment at this point, it will be equal to the deflection of the real beam at that point. And similarly, the shear force at any section of the conjugate beam is equal to the slope of the elastic curve at the corresponding section of the real beam. And now a very important question comes again: what is the sign convention? Because there is no point in talking about structural analysis without the sign convention. I mean, if you mess up, if because the most important thing again uh, in bending moment is the sign, because most buildings we see around us are concrete buildings like RCC, reinforced cement concrete, and concrete is very weak in tension. So if we are analyzing a beam, we have to know on which side tension is coming and on which side compression is coming, because on the tensile side we have to give the steel reinforcement to take the tension. Concrete is supposed to be strong in compression. So if we are sure that one part of a beam or a column will only be always be under compression no matter what the loading condition is, then we need not give any steel, and that is how we make a design economical. So sign is very very important in structural analysis, in deflection, in slope, in shear force, bending moment, anywhere. And this is the sign convention. This is simple because positive shear force in the conjugate beam equals to positive slope in the real beam, and positive moment in the conjugate beam equals a positive deflection, upward movement. We have taken upwards as positive. So these are the steps. I mean, as summary, first we draw the real beam with all its loads and support conditions. Then we determine the support reactions using the equilibrium equations, and now we draw the conjugate beam. I mean, we determine the support reactions, and from that we get the bending moment diagram. And to draw the conjugate beam, we use that M by AI diagram as the loading. We apply the boundary conditions as the rules we specified, that hinge support remains hinge, fixed support becomes a free end, and all that. Then we solve for bending moment using the concept of virtual work or anything. I mean, there is no need to use the concept of virtual work here. We know how to find out the, I mean, moment at any section. That is very direct. We can just use the principles of static equilibrium to find that, or we can draw the entire BMD of the conjugate beam as well, and we convert this back to the real beam using that. We convert the obtained bending moments and shear forces into displacement and slope of the real beam. This is an example. This is the example that I showed before, basically. So we know how to convert this into a conjugate beam. The length remains the same. The loading is as per the M by EI diagram, and the support reactions, the free becomes the fixed and the fixed becomes free. So now we are asked to find the slope and deflection at the free end, at this tip, at this A of the cantilever beam. So basically, what do we have to do? We have the conjugate beam. We now need the bending moment and shear force at this point. Just that. We don't need to draw the bending moment diagram because we are asked about only one point, and this is also the support reaction. So basically, we have to find out the support reactions. The MIA diagram, we draw the bending moment diagram for the beam and divide it by the flexural rigidity. Because this is a new term. This EI is called as a flexural rigidity. Flexure is bending and flexure are synonyms basically. So EI is a structure's stiffness against, not stiffness. Again, I mean, its rigidity is, if you divide rigidity by length, you get stiffness. So flexural stiffness of a beam is EI by L, and flexural rigidity is EI. So we divide by that to obtain the M by AI diagram, and we get the conjugate beam that is loaded in that way. And this is a description of how the conjugate beam has been made. And the M by AI diagram is applied at down as downward loads in the in the conjugate beam, because this M by AI diagram was negative. We know that hogging moment is negative. So this is this is how we have drawn the conjugate beam. Now, to find the slope at A, we need to find the shear force of at A in the conjugate beam. The shear equals to this. This is the, I mean, the shear force at this point will be the support reaction basically. So support reaction, since there is only one, if I mean that if you apply the equation of equilibrium, delta Fy is 0, what is the total vertical force applied on the beam? That is half this, that is basically the area of this triangle, and the area of this triangle is half into 12 into this 36 by EI, and that is applied downwards. So at the support there will be an upwards reaction. So The shear force at A is half, VA is half into 12 into 36 by EI. This is in the upward direction. So the slope in the real beam at point A is positive. That is, I mean, you divide by EI. If you divide by the values of EI given, you will get this value. And this, since it is positive, this is anti-clockwise. That is the general sign convention we follow. Anti-clockwise slope is considered positive, and upwards deflection is considered positive. So this is how the slope of the beam will be, and you can try to visualize this as well. When we apply a force in this in this real beam, forget about the conjugate beam. In this beam, at the tip we have applied a downwards force, so the deflected shape will be something like this. The deflected shape will be something like this, and the slope will be anti-clockwise. I mean, this was originally like this. It has come somewhere here. So this will be the slope, and this is anti-clockwise slope. So the sign convention is matching. Now we want to find the deflection also at A. So for that we need the bending moment at A. For the bending moment, what do we do? There is again only one support reaction, so there will be one moment here that has to balance the entire moment given by this force. And this, the magnitude of this force is half into 12 into 36 by EI. And the effective point of loading, like in a UDL, if this had been a uniformly distributed load, that is a rectangular load, we would have applied the equivalent load at the midpoint. And since it's a triangular load, we are applying this point, the equivalent load, at a point h by 3 from the base of the triangle. With that we know that is the centroid of a triangle is a one third from the base. So if this is 12 feet, one third of 12 is 1/12 is 4 feet. So the equivalent load will be at 4 feet from B and 8 feet from A. So the moment will be the total magnitude of the force into 8. That is what 8 is like 2 by 3 into 12, because it's 2 by 3 from the tip of the triangle and one third from the base of the triangle. And this is negative because this is how your when we are coming from this side, when we are coming from the right side, we know anti-clockwise moment is positive. Like this, the sign convention. Let's go back to that once. This is the sign convention. When we are coming from this side, like the right side, this is positive. This moment, anti-clockwise moment, but here we are getting clockwise moment. Here we are getting clockwise moment in this. Like this is the force, and about this point we are considering. So it's like this. It's a clockwise moment. That's why we are taking it as negative, minus half into 12 into 36 by EI, which is the magnitude of the force, into 2 by 3 of 12, which is this. This is a negative. This is a negative moment. We plug in the values of the E and I, and we get this 37 0.37 inch. And this is negative, so it means downwards deflection. And if you look at this diagram, of course you understand that if I apply a force at this tip at a point to point load, it will obviously deflect downwards. So the sign conventions are matching. And do keep in mind here that anti-clockwise slope is positive here. It has nothing to do with the sign convention of bending moment. In bending moment, sign convention is seen as, if you come from the left side, clockwise moment is positive. If you come from the right side, anti-clockwise moment is positive. But for slope, always anti-clockwise angle, like rotation, anti-clockwise rotation is positive. And again, I say that sign conventions are never fixed. Like sign conventions can never be imposed. If you Even if you change sign conventions, you have to get correct answers. But for that you have to change the sign conventions everywhere. Like in the conjugate beam, the kind of sign conventions we assume, that positive moment means positive slope, negative moment means negative slope, all that has to change. So it's better to follow a certain set of sign conventions that you learn now and stick to it for the rest of your life, because otherwise there's unnecessary confusion. And we look at another example. Here, the this is a simply supported beam. We have to determine the slope at the support A and the deflection under the concentrated load of this beam. Like this point will of course have no deflection, and we need to find out the slope at this point, the support point A, and the deflection at B. This is the real beam. If you convert it into a conjugate beam, what will happen? The length will remain the same. The the length will remain the same. Simply supported, like this hinge and roller will also like remain the same, because in as we saw for the rules of boundary condition, hinge support and roller supports remain the same. in the conjugate beam from the real beam, and we have to draw the bending moment diagram. By now, I mean, the bending moment diagrams, you should understand the nature of the bending moment diagram just by default, because if you have practiced as it was, I mean, covered in week one, I think it is obvious that the bending moment diagram will look like this. But of course, if you are not yet comfortable with drawing the bending moment diagram directly, you can use the basic, the way we had started, like finding out the support reactions, taking a section x from this end and finding the moment and then plotting it. It will look like this. At this point, it will be maximum 180, and we divide it by EI to get the M by EI diagram. And this one is positive. Okay, this is sagging moment. Sagging moment means that makes a structure bend like this, like a clothesline or something. This is the force. I mean, this is the applied the moment. So it is since it is positive sagging moment. This is an upward load. This is an upward triangular load. Now, this is a kind of loading condition that we don't usually see in beams. In beams, mostly, I mean, in real life beams, mostly they are loaded downwards. But in the conjugate beam, it is an upward load here. Don't be rattled by that, and treat each conjugate beam in its own merit. If there is upward load, there is upward load. You have to be careful about the conditions and about the sign, and not just like have a bias that if the shape you get, but also be careful about the sign. Don't just assume it's downward load, because there is a tendency for us to assume that a beam will always be loaded downwards. So anyway, this is the conjugate beam that is loaded with a triangular load. And what do we want? We want the slope at support A. So for that, we need the shear force at A. We first draw the bending moment diagram for the beam and divided by the flexural rigidity to obtain the moment curvature in by ear diagram. In the conjugate beam we have drawn, and now we need the reactions for the conjugate beam to get, I mean, to get the shear force at A is basically the support reaction at A. So the reaction at the supports of the conjugate beam will be uh, this will be basically, since this is a symmetric structure, like in a beam, roller support and hinge support are equivalent, because a roller support allows this horizontal movement, I mean horizontal displacement. But in a beam, since there is only transverse loading and no axial loading, there will be no axial displacement. So a hinge and a roller are equivalent. And so the loading conditions is also like symmetric, like about this point B, it's symmetric. So the reaction at A and the reaction at C will be equal. That will be half of the total load of the beam on the beam. That this the total load on the beam is the area of this triangle, that is half into 30 into this 30, because that's the total length of the beam. So half into 30 into 180, 180 by EI, and you put a half due to, like, on each support there will be half. And the reaction is negative, of course. Like, again, in simply supported beam, in normal simply supported beams, the reactions are always in the upward direction. So don't blindly put that. Since the loading here is in the upward direction, the support reactions will be, of course, in the downward direction. So at A we get this minus 1350 by EI. That this is the units. And so the slope at A in the real beam is the force at A in the conjugate beam. The shear force at A in the conjugate beam is this, as we found out. So the slope of the at support A in the real beam will be this. Like, put in the value of EI and we get this value, and it is negative. That means it is clockwise. Like, the rotation is in the clockwise direction, clockwise sense. So this, like this. And let's try to visualize that. When we apply this force, forget about the conjugate beam. Now we are talking about the slope in the real beam. So we apply a concentrated load in the center. The ABC will, one second, ক্লাস নিচ্ছি, তোমাকে একটু পরে ফোন করছি, ঠিক আছে বন্ধুরা? Right. If we apply a concentrated load at this point, this ABC, like, the beam will deflect in some manner like this. Like, it will, you can see that, you can visualize that. Of course, we don't know the exact values, but the shape will be like this. So at A, how is the slope? Like, this was originally the original slope at A was 0 degree. Then it bent like this. It became something like this. So rotation is in this sense, and this is the clockwise sense. Like, uh, it is bending in this sense, rotating in this sense. So this is the clockwise slope. Sorry, not moment. So this. 0.0084 radian is in this. And also remember that you are getting in radian, don't write degree because radian is the natural unit. So if you follow this method you will get in radians, and the deflection you will get in whatever length, whatever unit of the length you have put. So here you will get in feet basically. And this, I mean, in this I, like this I is given in inches, that we have to be consistent. In the European European units, they usually use this uh, inch and pound, feet, these, but in Indian standards we use kilonewton meter. So I would say just convert everything into newton and meter or something. Like you can use kilonewton as well, but stick to the same units. Like if you use newton and meter everywhere, then you will get the deflection in meter, and it will be a very like of the order of 10 to the power minus 3 or 4. So you can multiply it by 1000 and uh, express the answer in form of millimeter, which is generally what is expected. And now for deflection at B, we want the bending moment of the conjugate beam at B. So for that, what do we do? At this point we need the bending moment. At this point we know the support reaction, and to find the bending moment we use the usual method. Like this is 1 by ei is taken common. This is the support reaction into 15. This is the support reaction in the downwards direction. Like this is the support reaction into 15, because the this force has provides a moment of the magnitude of the force into 15 about this point B, and that is in this clockwise, that is in the anti-clockwise direction. And when we come from the left side, and clockwise moment is positive, so that is negative. So the contribution of this support reaction will be negative, and we are coming from one side. Now we are not going to consider the C, of course. We take a section at B. We are trying to find out the bending moment at B, so we are coming from the left side. You can also come from the right side, you will get the same answer. So we take the contribution from this support reaction, and then we have to take the contribution of this triangular load, not this part. We have to take only the part between A and B. So the magnitude of this part is half into 15 into 180 by EI, and the point of action will be this, like from 1 by 3 of the of this length from the base. So it will be 5 feet from B and 10 feet from A. We are taking the moment about B, right? So we have to take 5 feet, like 1 by 5, 1 by 3 of 15. This is minus, as we talked about, minus that support reaction force at A into 15, plus half into 15 into 180 into 15 by 3. Why is it plus? Because this moment, this equivalent force is acting in the upward direction, and about B it gives a clockwise moment. And when we are, since we are coming from the left, the clockwise moment is positive. So this is the value we get, negative. So the deflection of B in the real beam will be in the downward direction, and we put in the values of E and I and get this in inches. Because we put this, because we put everything in inches. So, and trying to visualize it again, forget about the conjugate beam. When you apply a point load here at this midpoint or at any point, it will deflect something like this, and the B point is obviously going to deflect downwards. So that is why we are getting negative. Like we are getting we are getting negative slope, that is in the clockwise sense, and we are getting negative deflection in the downwards direction. Now we look at a brief summary of this chapter that we completed. Is deflection of beams. First, this is the governing differential equation of a beam, of an Euler-Bernoulli beam. There are some assumptions that we discussed last class, and they are important. The assumptions are maybe asked in an exam or something. So just read that theory a bit. That EI d2y dx square is mx, where y is the transverse deflection and x is the distance along the axis of the beam. So an m of x, m is of course a function of x, the bending moment varies along the section. So ei y dash dash is mx. This is the governing differential equation. One way to get the this profile is a method of double integration, which is the most basic method. This method involves integrating the equation of elastic curve twice. Of course, if you integrate it once, you will get the expression for dy dx, and dy dx is the slope. And so the first integration is the slope, and the second integration gives the deflection. And since this is an indefinite integral, you will get two constants of integration. Like when you integrate once, you will get one constant of integration, and then twice you will get another one, like c1 c2 suppose. And those constants will be determined using the boundary conditions. Like for this beam for this beam we have two boundary conditions, that if we take x from A, then deflection at A and deflection at B are 0, right? So y of 0 is 0 and y of L is also 0. So if you put x equal to 0, you can put y equal to 0 in this equation, and if you put x equal to L, you can also put y equal to 0. So you will get two equations in C1, C2, you can solve them. So you get a y of x expression and a y dash, that is the slope expression. So you basically know the entire profile, you know the slope and deflection at any point. This is the most basic and the most lengthy method, so we generally don't use it. To make it simpler, we have they are I mean people have developed easier methods. The one is a moment area method, where this method uses two theorems to determine the slope and deflection at specified points on the elastic curve of a beam, not the entire beam at once. You have to find out, like, whatever point we have been given, you have to choose accordingly. The two theorems are as follows. The first moment area theorem states that change in slope between any 2 points on the elastic curve of a beam equals to the area of the M by EI diagram between those 2 points. This is what it says. Like, this is the suppose a cantilever beam loaded at the tip. This is the M by EI diagram, this a negative one. So A and the slope at B remains 0 because this is a fixed support. The slope at B remains 0, and and there is some slope at A, and you can visualize it, like, since it deflects in this manner. This rough deflection you can visualize, right? And this deflects in this anti-clockwise sense, and so theta A minus theta B will be the area between the M by AI diagram. The second area moment area theorem says that vertical deflection of point A from the tangent drawn to the elastic curve at point B equals the moment of the area under M by A diagram between these 2 points about point A. This actually has a lot of clauses, like, uh, if if you want the deflection at point A from the tangent at B, then you have to take the moment of the M by A diagram about the point A, and the M by A diagram between these 2 points about point A. It's easier to say diagrammatically. So this is the M by A diagram of this equation, of this thing, like this loading condition. And here the tangent drawn to the elastic curve at point B is a straight line, is a horizontal straight line, because this is a fixed end and there will be no rotation. And so this is the tangent, and this is the deflection of A. So delta A slash B stands for that the distance between the tangent at B, wherever it intersects at A, and the deflection at A, the distance between those two. Here, coincidentally, since that this tangent is a horizontal one, delta A slash B is equal to delta A, but the tangent could also be an inclined line, right? So we have to take the area of this n by ai diagram between A and B about A. So this x dash is this x dash is the uh, point of the triangular load has an equivalent application at one third from the base. So if this was L, then this x dash will be 2 by 3 L, and we can find this, delta A by A slash B is as area of the n by a diagram into x dash. And finally, we look at the conjugate beam method that we covered now. The conjugate beam has been defined as an imaginary beam with the same length as that of the actual beam, but with a loading equal to the M by A diagram of the actual beam. The supports in the actual beam are replaced with fictitious support with boundary conditions that we studied earlier, that will result in the bending moment and shear force at a specific point in the conjugate beam equaling the deflection and slope respectively at the same points in the actual beam. This is another example, uh, just in a schematic manner. It has not been solved. If suppose 2 point real loads are applied here, the bending moment diagram will be of this nature. If it is difficult to visualize, again you can just solve for the support reactions, and you can take like three parts in one AC, CD, and DB. You can find out the expression of the moment as a function of x, and you can draw. You will see that it will be like linear in these two portions and constant here. So that, and this is positive because it is sagging moment. Sagging moment means positive moment, because it will reflect like this, you can see. So this is there will be an upward loading in the conjugate beam, and you can find the slope and deflection at any of these points by finding out the bending moment and shear force at any of these points on the conjugate beam. So that's all for today. Do you have any questions? Okay, if there is no question, you can leave. We are ending the class now. The next class in week 6, we will look at influence line diagram. That is uh, a very different kind of concept from the ones we have seen so far.